Welcome back to Calculus 1, and mostly we are done with the definition of derivative. We say the derivative, it is the slope of a tangent line, which is a limit. So derivative, it is a limit. And also, if you recall, this is a definition we provided from the previous section. And indeed, I want to note here is this a really could be of any value. Okay, at x equals a could be 1, could be 2, or negative 1.5, any value in the domain of the function. So why not, well, simply why bother with a? Okay, because a could be of any value. Why not simply using the notation x? So indeed, this is what we do. F prime of a is such, so we simply can write it as f prime of x, f prime of x. And I hope you realize to this moment, okay, when we are having a function f of x and then f prime of x, it is also a function. F prime of x, it is also a function. So f prime of x, it is still defined as the same limit of the difference quotient. And f prime of x, it is the so-called derivative function of the function f of x. And I have one more example from here. Say this is still the example from the textbook. F of x equals square root of x. We want to calculate the derivative, and indeed, actually, I think in our previous section we calculated f prime of a. Now we are just calculating f prime of x, and we'd like to emphasize the derivative itself. It is also a function. Okay, so f prime of x, according to the definition, and it is a limit. And again, it is always true, such a limit, you cannot apply the direct substitution for such a limit. And then, because of the radicals, we consider using the radical conjugate. Actually, this part should be correct. This is plus, it is the radical conjugate. And then also you have to do the correction for the denominator, the radical of the conjugate. Put the same radical of the conjugate to the numerator and the denominator. And then the numerator part, the product of the conjugate pair, it is a product of sum and the difference, which turns out to be difference of squares. Square root squared, that's x plus h. Square root of x squared, that's a single x. X minus x is cancelled, and there's only one single h left on the top, and furthermore, there's another h in the denominator. So in the end, this is what I realized. The limit, it is in the fashion of 1 over square. Actually, I still need to correct. This is supposed to be the radical conjugate. It should be plus. It should be plus, okay. Should be plus. 1 over the square root plus the square root. And this limit, it is a situation when we are considering for any value of x as h approaching to 0. Fix the value of h as fix the value of x as h approaching to 0. So you replace h with 0, and it turns out to be 1 over 2 times square root of x. This is the derivative of the square root function. It is 1 over 2 times square root of x. It is calculated using the definition. It is calculated using the definition. And next week, we are going to, match this result with the formula, the so-called power rule for derivatives. But anyway, for now, let's try to remember. This is calculated from the definition. The derivative of square root of x is 1 over 2 times square root of x. One more example from the textbook. We have different function. F of x equals x squared minus 2x, a quadratic function. And now I understand, hopefully we understand, the derivative, it is the limit of difference quotient as h approaching to 0. X could be of any value. And also it is always a situation the denominator is 0 when we consider direct substitution. Okay, so it doesn't always require some extra work. So what I did here is first I replace each x with x plus h, and then minus f of x I copied on the formula, and then for this perfect square part I expanded into 3 terms, and also I multiply this out, and also I took away this pair of parentheses. As you can tell, many terms canceled. X squared minus x squared, they cancel. And also I think there's minus 2x plus 2x, they cancel. So there are 3 terms left for the numerator. 2xh plus h squared minus 2h. And I hope you see h is a common factor for the numerator, right? Which means that h can be cancelled by the denominator h. So I'm still having 3 terms left, 2x plus h minus 2. Certainly the denominator h, it is already cancelled, okay? And one more time, to find out a limit, this is the only reliable way to find out limit, plug in value, direct substitution. Okay, this time we are considering the limit as h approaching to 0. So we replace h with 0. It works perfectly fine. And we are having this as 2x minus 2. So indeed, for this problem, we are saying the derivative of x squared minus 2x is 2x minus 2. It is calculated from definition. And for now, in those 2 sections, 3.1, 3.2, you are required to calculate derivative using the definition as the limit of difference quotient. I know a lot of us know there are better ways to handle the derivative instead of the definition. Again, I want to say for those 2 sections, 3.2 and 3.1, you must use this way, use definition to calculate the derivative. 3.1, 3.2. 3.2, mostly we are trying to say the derivative itself is a function. Okay, so whenever you have a function, it is always possible to consider the derivative. So I'm saying it is possible when you have a derivative as a function, you can consider the derivative of the derivative. F prime of x, it's the so-called first order derivative. F double prime of x, it's the second order derivative. Or put in words, it is a derivative of the derivative. Certainly, sometimes we may consider the third order derivative. F triple prime of x, that's the third order derivative. Okay, it's easy to denote the derivative with primes. Single prime, double prime, triple prime. But anyway, somewhat there is something missing here. The derivative using prime notation. Okay, many times we may have a function of time t or distance s or some other variables. So sometimes we do write a derivative in other ways. And it's a DD notation. Y is a function of x. Certainly we can write this as y prime or f prime, they're all the same. And also we want to emphasize we are considering y as a function of x, it's dy dx. And dy dx, really take a close look. I say dy dx takes more space and it takes more time to write. But anyway, it doesn't match perfectly to the actual definition, right? You see, this is definition of the derivative. On the top, really it is the change of y. That's dy. A tiny change of y. At the bottom, it's a change of x. A tiny change of x. So precisely, we write derivative as dy dx. And also, we could use this dd notation to denote the second order derivative y double prime, which is f double prime, which is d2y dx2. And we will talk about those higher order derivatives later. And for now, at least I want you to know there are two ways to denote derivatives: f prime notation and the dd notation. And also, I am saying somewhat dd notation, it is better. It is better, okay. So I say actually this is mostly about section 3.2. 3.1, 3.2, they offer the same topic, the definition of a derivative. Derivative, it is a slope of a tangent line, and it reflects the instantaneous rate of change of a function. And the derivative also can be considered as a function. Later on, we will have those so-called higher order derivatives. Basically, they are the derivatives of derivatives, like the second order or the third order. Thank you for watching. Next time, we will introduce some derivative rules and formulas, so we don't have to bother with the definition. Honestly, it's just true. The definition calculation, it is very time consuming, and it is very complicated, as you can tell. All the examples, they all require actual work, because derivative is a limit, but anyway, those limits cannot be evaluated using the direct substitution. They always require actual work. So next time, we are going to introduce some rules and formulas, make the derivative calculation easy. Thank you for watching.